Hey guys, welcome back to my channel, and in today's video we are going to solve one more interesting LeetCode question, that is question number 19. Remove nth node from end of list. So this question has been asked by these many companies in last 2 years. So let's see what this question is all about. So we are given head of our linked list and we have to remove the nth node from the end of the list and return its head. So if we see this example, so in this example we are given a head of a linked list which consists of all these values, and we have been asked to remove the n equal to 2, that is the second last node from this linked list. So once it is being removed, this linked list will be something like this. So if we see what exactly data structure linked list is all about, then there is no such concept of indexing as. Linked list works on two primary things, and that is referencing and redirecting. So if it's working on these two things, then how we are going to work with some sort of indexing part? Because if we see, we are given some sort of index or a negative index, where n is 2, it means the second last index from the last of the linked list. So if we have to come up with any such solution in which we have to deal with the indexing part of the linked list, so firstly we need to calculate its length, right? At least the greedy approach with which we are approaching the solution is consisting of this kind of mentality, where we can firstly calculate the length and then afterwards we will see how we can deal with this nth value. So before that we need to calculate the length. So if we see this example, what I will be doing is, firstly we are given the head of the linked list, so we need to calculate its length. So we will traverse this whole linked list once and calculate its length. So the length will become 5, right? So I will start from 0 and I will come up to this place where my length is 5. So I traverse this linked list once and calculated the L. Now the n is given 2. So what I will do is, I will simply subtract n from L. So what I will get is L minus n, and that is 3 in this case. So if I'll see the third node or the third index, so in general how we index the array or any data structure is starting from 0. So if I'm going to see on third index, we are getting the node which is the second last node which we need to remove, right? But if I'll see the number of node or the third node, I know that if I have to remove any node from a linked list, I don't have to delete it or do any such functionality on that node. What I have to do is, I have to simply update the previous node's next pointer. So rather than pointing towards that node, this node will now point towards the next node. So L minus n is giving us the number of node or the position of the node where we need to update its next pointer, right? So what we will do is, we will firstly calculate the length of node, then we will calculate L minus n minus 1. So we will get the index of the previous node from the target node, because we will simply update the next pointer of the previous node, and then our target will be achieved without making any change to target node. So this is the first approach, and after redirecting this pointer, this linked list will become something like this. So the first approach that we came up with was, firstly calculate the length, and after calculating the length, calculate the index of the previous node, which we did by L minus n minus 1. We are doing minus 1 because we want the previous node rather than the exact target node. This will give the exact target node's index, but we need minus 1 because we want to have the previous node's index, and we will update its next pointer. So this is the first approach. So if we see, The time complexity of this approach is, firstly we are traversing and calculating the length, so time complexity for that will be big O of n. Then what we are doing, we are again traversing L minus n in order to reach this place, this node where we need to update the next pointer. So again we will be traveling big O of L minus n. So if I am going to solve this whole equation, what I will get 2L minus n. So the time complexity will be big O of L. So what we got after solving this approach is time complexity of big O of L, and space complexity will be big O of 1, because we aren't using any other data structure. We are simply using these variables, so these are constants. So let's quickly see the code of this approach. I'm not going to code the whole solution. I will let you go through this whole solution just for the sake of video's length. So firstly what we did is we created a dummy node from list node, and then we assigned head to it. Then we are creating a variable length equivalent to 0, which will store the length of the linked list. Then we are having another node which is first. Now we are running a loop while first, and with this part we are calculating the length. We are simply updating the length variable plus equivalent to 1, and we are updating the first node with first dot next. And at the end of this loop, what we are doing the same thing that we saw in our example, length minus equivalent to n. And after this we will again assign dummy equivalent to first, or first equals to dummy, because now we are again going to run this loop, and we will traverse this whole linked list again, not whole but L minus n part, just to reach the position of that node where we need to update the next pointer. So we will again run a loop while length is greater than 0. We will decrement a value from length. We will update the first pointer. As soon as the length becomes 0, this loop will break. We will step out, and at that point of time we will be exactly at this position, third node position, and we are saying first dot next will be first dot next. This is the part where we updated the next pointer, and then we will return the head of the linked list. This was the first approach, and it was of big O of L time complexity and big O of 1 space complexity. But we are traversing this whole linked list twice, or the nodes twice. So can we do a bit better than this? So yes, we can do better than this. Rather than traversing this whole linked list twice, we will be only traversing it once. But as in this case, we were using only one pointer while traversing. In the next approach, we are going to use 2 pointers, and I'll show you how we are going to optimize this same approach but with 2 pointers. Now let's see what our second approach is. So in second approach, what we are going to do is we are going to have 2 pointers. So our n was 2, and we are going to have 2 pointers. First one is slow and second one is fast, and both are currently equivalent to head. Now what we will do is, firstly we will make sure that these 2 pointers are at a distance equivalent to n. So there has to be a distance between these 2 pointers, and it is going to be equivalent to n. So for that we will run a loop, and our slow pointer will be at this place, but our fast pointer will be at this place. So we will run a loop, and we will move our fast pointer by n steps, so it will be at this place. Now we have to maintain this distance, and we will again move ahead, but this time we are not going to move with only one pointer, we are going to move both the pointers. So this will go to this place, and this will go to this place. Slow will go to 3, and fast will be at 5. So as soon as slow reaches this node, fast will be at the last node, correct? And now we can see that fast can't move ahead because it is having a null node. This is the end of our linked list, so we can't move any further. So as soon as we end up at this place where our fast pointer can't be moved further, we will notice that our slow pointer is exactly at that place where we need to update the next pointer, right? And then we will simply update the next pointer of this node. And this is the approach 2 of this solution. Now some of you might have a question, not now but maybe after the coding part of this question, because firstly we are traversing and moving our fast pointer by step n using a loop, and then again we are going to use a loop for updating these two pointers and move them simultaneously so that fast one will reach null first. So in this case also we are using two loops. Then why this approach is better than the previous one, right? What's the difference? So if we see both the approaches, in previous approach we were using two loops, but in those two loops we were visiting the same nodes twice, right? We were visiting those nodes twice, but in this case we are simply running that loop, and after our fast pointer is updated and the distance is maintained, we are simply maintaining the distance between these two nodes, and then at the end we are updating the next pointer. So in this way this approach is of time complexity big O of L, where L is the length of linked list and space complexity is again big O of 1. So this is also having the same time complexity, but we don't have to pass through this linked list twice in this case because we are using two pointers and we are going to work with them simultaneously. So we don't have to go through this linked list twice, and that's why this approach is better than the previous one. Else than that, if we see the space and time complexity is same and the output is also same. So now let's quickly code this solution. I think I hadn't run the previous code, so let me just submit this. And you can see that the previous approach as well was accepted. It's not like that this code is not going to get accepted. Both the approaches are accepted and the code are going to run. But the approach that we have just learned, let's now code that one as well and see. So let's define our two pointers, that is slow equals to fast equals to head, and then what we will do is for I in range n, fast equals to fast dot next. After this we are saying while fast dot next, correct? To the point there is a node after fast, we will move ahead. So slow will be slow dot next and fast will be fast dot next. We just need to reach the endpoint, and as soon as we reach the exact position we need to update the slow pointers, slow dot next dot next, and this is it. We just need to now return the head. But there is one edge case which we need to check before this step, that is if not fast. So what this step is checking, suppose there is only one node. Suppose there is only one node in a linked list and that is the one that we need to delete, right? So in that case when we have moved a fast pointer, it must have reached the last node, correct? It is already at null. So this step will check if our fast pointer is at null, simply return head dot next, because this while loop won't work in that case. So now let's try to run this. Okay, here I made a mistake, that is slow.next will be updated with slow.next.next, right? Because we are updating the next pointer of it. So yeah, so this is also accepted. So now quickly code Ruby solution of this approach. So in Ruby as well, we will do the same thing, that is slow equals to fast equals to head. After this, we are saying up n dot times update fast with fast dot next. So this is how we will update our fast pointer. After this, we will add that edge case. So return, rather than adding if, I'm just writing return head dot next if there is no node, if our fast is at null, right? And after this, while loop, while fast dot next. Inside this loop, we were doing slow will be updated with slow dot next, and fast will be updated with fast dot next. Outside of this loop, we updated slow dot next with slow dot next, and then we return head. So now let's quickly submit this as well. So yeah, you can see this is also accepted. So these were the solutions with two approaches, and we realized how sometimes only a change of pointer or a small mathematical change can bring a huge difference in our approach. Sometimes the time and space complexities are same, but still the traversal part and how many times we are traversing those arrays makes a small difference. But yeah, these small differences are something which will set us apart in our interviews. So I hope this video was helpful for you all, and if it was, then don't forget to like, share and subscribe my channel. I will soon come up with more such questions. Till then, keep messing with algorithms, and thanks for watching.